LeChatelier's principle and solubility equilibrium. LeChatelier's principle is basically a system to allow us to predict what's going to happen to a reaction that's in equilibrium. When we change concentration, add an ingredient, remove an ingredient, when we change the temperature, when we change the pressure on the external container, so the pressure pushing down on the reaction, when we change the volume of the reaction vessel, those changes will affect what's happening to a system in equilibrium, and LeChatelier will allow us to predict what the system's going to do to counter that. All your answers for LeChatelier problems will be one of three. Shift right, make more products, or shift left, make more reactants, or sometimes there's no change at all. A homogeneous equilibrium reaction is when all your reactants and all your products are in the same state. They're all solids, they're all liquids, they're all in the same state. They're all aqueous, they're all gas. Heterogeneous equilibrium reaction is when you have a solid or a liquid. Change in concentration. This is also true for change in temperature. There's a little sayings: add away, remove towards. If you add a compound and it happens to be a reactant, then LeChatelier is going to predict, since you're adding something, equilibrium will shift away from what you added. So if you add a reactant, it's going to shift away from the reactant. It's going to shift towards the product side. So we say, if you add a reactant, LeChatelier will predict it'll shift right and make more products. If you remove a reactant, you're removing something, a reactant's on the left side, add away, remove towards predicts. If you remove something, that's a reactant, it's going to shift left and make more reactants. And again, solids and liquids don't count. Just don't even include those in your equations. For temperature, same thing works still. Add away, remove towards. If the delta H is a positive value, heat would be written as a reactant. If the term endothermic is used in describing the reaction, heat is a reactant. If delta H is negative, heat's being given off. Heat's a product. If the term exothermic is used, then heat's a product. You would write the word heat actually in your equation and then apply add away, remove towards. Could you put a container that a reaction's happening in an ice bath and cool it? Sure. So that would be removing heat because you're cooling it. So you would take a look at the conditions the reaction's happening in, whether it's exothermic or endothermic, and then apply add away, remove towards. External pressures. These are only gases, of course. And what we're talking about, these are cylinder problems, very similar to what happens in physics. And I link external pressure and volume always together. Because if you push an external pressure like on a cylinder or even a balloon, the cylinder is going to compress, the volume is going to go down. So as the pressure goes up, volume goes down. As the pressure goes down, the volume goes up. And you have to think of everything in terms of gas molecules, only gas molecules. If the volume goes up, the reaction is going to shift to whichever side is going to produce more gas molecules. So you look at all the molecules, reactants and products that are gases, look at their stoichiometric coefficients, and whichever side has more of them, more gases, if you're making the volume larger, which means decreasing the pressure, then it's going to shift towards the side with more gas molecules. The opposite also holds to be true. Okay, so a change in external pressure or volume. The expression written at the bottom. If we increase the pressure. Pressure, arrow up, which means volume is going to be decreased. Volume, arrow down, which means the number of gas molecules have to decrease. Volume and gas molecules go in the same direction, which is opposite pressure. So if you decrease the pressure, that means you're increasing the volume. You're going to need more gas molecules and increase the gas molecules. LeChatelier predicts it'll shift to whichever side has more gas molecules. Adding an inert gas. If you add an inert gas, always focus on the volume of the container. If the container is like a stainless steel container, a fixed volume, a scuba tank if you would, if you add an inert gas to that, the reaction doesn't see the volume in the container change. It doesn't recognize the inert gas because it's not part of the reaction. So since it doesn't recognize a volume change, there's no change in equilibrium. Now think of a balloon. If you had a reaction happening in a balloon that could expand or decrease, if you added an inert gas, if you add any kind of gas to a balloon, the balloon's going to get bigger. The reaction still doesn't recognize the inert gas, but what it recognizes is a change in volume. So that reaction in equilibrium, all it sees is the volume get bigger. It got bigger because of the inert gas, but it doesn't care. The reaction doesn't care. It sees the volume get bigger, so it's going to shift to create more gas molecules. We discussed this earlier. Change in temperature is exactly the same as the change in concentration. Add, away, remove, towards. And you can actually write the word heat as a reactant or product. Endothermic, which means delta H is a positive value, I'd write the word heat as a reactant. Exothermic, which means it's giving off heat, delta H would be a negative value, write the word heat as a product. Add, away, remove, towards. Catalysts. Catalysts lower the amount of energy needed for a reaction to occur, but it has no effect on equilibrium. It doesn't change the amount of ingredients you need, it doesn't change the amount of reactants, and it doesn't change the amount of products produced. Only thing it does is make the reaction easier to occur. KSP. KSP, KEQ, KA, KB, KC, KF. There's about 5 more Ks. K is always K. Products raised to their stoichiometric coefficients divided by reactants raised to their stoichiometric coefficients. Never write solids or liquids. So KSP, which is the solubility product constant, it is a solid being dissolved in water. Water's a liquid. Reactant solid. Reactant liquid water. Products, both aqueous. Your KSP is nothing more than those ions raised to their stoichiometric coefficients. If you like, which says never write solids or liquids, just put the number 1. If you still want to have a fraction, products over reactants, anytime there's a solid or liquid, just put the number 1 into the equation. It'll work the same way. It might flow better for you. The larger the K value, the more soluble the compound, the easier the ions come apart. These are some problems in the back of the book in page 512 that you should be doing. They should be assigned for homework. 30, 32, 34, 35, 36, and 38.